and welcome to this presentation on modified Q-learning algorithm for rate profiling of polarization adjusted convolutional codes. My name is Samir Kumar Mishra and this is a co-work with my colleagues Digvijay Katyal and Sarvesa Anigundi Ganapati. We all work at Samsung Semiconductor India Research. Here is the brief outline of this presentation. First, we will introduce polar codes very briefly. Then we will go to polarization adjusted convolutional codes. We discuss the encoding and decoding. And after that, we go for reinforcement learning based design for polar/PSC codes. We will show simulation and results, and we conclude with some open problems that we found during our work and which form the foundation of our future work. Polar codes introduced by Arikan are the first provably capacity achieving codes for the class of binary input memoryless symmetric channels with low encoding and decoding complexity of the order n log n for a code of block length n. Polar code is based on a phenomenon called channel polarization. Here, a communication channel is transformed into polarized subchannels which are either completely noisy or completely noiseless. We transmit information bits over a set of noiseless subchannels and we transmit fixed or frozen bits, in most cases zeros, over the noisy ones. Polar codes have already been commercialized for the 5G new radio for encoding and decoding of control information, that is new radio PDCCH. And here is an example of channel polarization wherein we are having an average channel which is W, and we perform some transformation which will create from two copies of W a channel W minus and a channel W plus. W minus is supposed to be a worse channel than W in terms of channel capacity. W plus is supposed to be a better channel as compared to W in terms of channel capacity. So as we do this process of polarization recursively from 2 to 4, from 4 to 8, 8 to 16, 16 to 32, 32 to 64 and so on, as the length of the overall block code increases, the recursive steps of polarization lead to a set of channels being completely worst and a subset of channels becoming completely good. So we will transmit information on the very good channels which are formed. We will transmit known bits on the worst channels. So let's say we have n polarized channels. Among them, we will select k best channels or good channels. We will transmit information bits on them. On n minus k channels, we will transmit 0. So here the code rate finally is k over n. Let's say I have to construct nk polar code. This means out of n transmitted bits, only k bits will carry information. The rest n minus k bits are going to construct parity. When we talk about polar code construction, what we talk is the procedure to identify k bit indices out of n bit indices which will carry this information bit, and we call them information bit indices. The rest n minus k bit indices carry zeros which are known to both transmitter and receiver, and we call them, according to the literature, frozen bit indices. So the game of polar code construction is all about selecting k among n channels. So the construction problem complexity is n choose k, which is, I think, is very complex problem to solve. However, there are a subset of channels like the binary erasure channel, which is identified by its erasure probability epsilon. For this binary erasure channel, polar codes can be deterministically constructed by the recursion, which I just spoke about earlier. However, for the EWGN channel, additive white Gaussian noise channel, it is not possible to construct polar codes very easily. This is because when we try to do the polar uh, transform or the process of polarization in AWGN channel, the alphabet of the output will grow explosively, and it is not possible to track easily all these exploded alphabet. That is why polar code constructions for AWGN channel are mostly based on heuristic algorithms, or they have been derived from LDPC literature such as density evolution, Gaussian approximation, and recently people have been trying to construct polar codes based on machine learning as well, which is the topic of our presentation. Before we go to polarization adjusted convolutional code, I want to give a brief history of how polar codes were developed and what kind of problems we faced. Here is a figure which describes the frame erasure rate performance of 12864 polar code variants. By frame erasure rate means if I transmit a k over n rate code, and on the receiver side, if I get at least one bit out of the capital K bits in error, then I declare a frame eraser. So, polar codes as shown by the black curve, uh, they are, compared to the other curves, they are very far away. In this figure, a figure with the curve which is towards the right symbolizes worse performance. The curve which is towards the left, as left as possible, signifies better performance. The red line shows the binary input AWGN dispersion bound, which is a theoretical bound on what we can achieve by transmitting a k over n code in a binary input AWGN channel. In this case, a half rate code of length 128 is being sent on the binary input AWGN channel, and the red curve shows what is the theoretical minimum FER that I can achieve. As it can be clearly seen, polar codes are far, far away from the theoretical bound. So, in order to improve the performance of polar code, Tal and Wadi from UCHD in 2011, they proposed CRC aided polar code under successive cancellation list decoding. So we will talk about successive cancellation list decoding. This is successive cancellation decoding is the paradigm on top of which polar codes have been invented, and polar codes achieve channel capacity under the paradigm of successive cancellation decoding, which means first we will decode U1 and next we will decode U2. We cannot do the reverse. The theory is based on this thing. So if we consider the bit channel W minus, the input to this bit channel is U1 and the output to this bit channel is Y1 and Y2. If we consider the bit channel W plus, U2 is the input and Y1, Y2, U1 is the output of the channel. So it is necessary that to decode U2, we need the decoded version of U1. So this is called successive cancellation decoding. Now, it was seen that if CRC was appended to successive cancellation list decoding, successive cancellation list decoding was invented as a method to improve upon successive cancellation decoding. A list of code words is output from the decoder. We place a upper limit on how many code words can be maintained in the list at a given point of time. Max is L equal to 32 in the figure. Beyond that, there was no improvement, so I did not put any curve for CRC aided polar code beyond L equal to 32. However, in a successive cancellation list decoding, we have to select the best path. However, how to find out which code word among the L code words in the list is best one? That is why Tal and Wadi proposed CRC aided polar code, where CRC bits are appended to the end of information bits, and by checking the CRC we can know where in the list the correct code word is present. This helped to increase the performance of successive cancellation list decoding under finite block length, and they beat for the first time the state of the art low density parity check codes, LDPC codes for short, and turbo codes, which have been pretty much the standard since the late 90s. However, the performance of CRC added polar code beyond L equal to 32 as shown in this figure, it does not improve much. The question is, for ultra reliability and low latency communications, how are we going to design better codes which reach this theoretical bound? One of the works in this direction was shown by Arikan in the Shannon Award lecture in 2019. On the International Symposium of Information Theory, Arikan presented polarization adjusted convolutional codes, which are significant improvement over the state-of-the-art polar codes. Arikan proposed sequential decoding, which have been used for decoding various block codes in the past. He showed that the FER performance of polarization adjusted convolutional code is just 0.25 dB away from the binary input AWG and dispersion bound approximation, the red color curve, at a target FER of 10 to the minus 5. Later, in a work from UCSD by Hanwen Yao and Alexander Wadi, both of whom are well-renowned researchers in the field, they showed that list decoding of Arikan's PAC code, which is using successive cancellation decoding, a similar performance can be achieved, but the list length is very high, like L equal to 128. And at L equal to 128 is very near the theoretical approximation bound. Now, I must mention here that no matter what we do, beyond L equal to 32, the improvement in CRC added polar code at this length is very difficult. However, PAC codes can achieve. So that is why a lot of interest was generated on the research how to design PAC code. Let's study the block diagram of PAC code. There are so many blocks. So let's first consider this one, the blocks under the dotted curve. If there was no PAC code, just polar code, the precoder unit becomes an identity, and this is also an identity matrix, which means we are not doing any precoding, convolutional precoding. We are just sending the bits after rate profiler into the polar transform, which is actually the encoder of polar code. Then we are modulating, let's say BPSK or QPSK modulation. We send over a channel and we receive at the receiver Y. The demodulation block generates the LLRs based on the modulation scheme, which are fed to the successive cancellation list decoder. The successive cancellation list decoder will output the decision matrix, which can be decoded as 0 and 1. Now, this dotted part is the polar code part. What changed in PAC code is the addition of these new blocks. First is the rate profiler. Second is the precoder. So, precoder and deprecoder are added difference from polar codes while discussing PAC codes. Precoder is on the encoder side, deprecoder is on the decoder side. Let's discuss rate profiler. The first step of encoding PAC code is called rate profiling, a term coined by Arikan. Rate profiler maps a vector of information bits denoted by D, which is of length capital K, to a vector of bits V of length n according to calligraphic I, which is the set of information bit indices. In other words, k information bits in D are mapped to positions in V which are indicated by calligraphic I. The uh, length of calligraphic I is k. So there will be indices on which we will place these information bits. The rest n minus k positions or bit indices in V are filled with 0. So these are the frozen positions. The selection of k indices out of n possible indices is called rate profile construction, which is the main invention of this paper. Two well-known rate profiling schemes are polar rate profiling scheme and Reed-Muller rate profiling schemes. Polar rate profile is based on Bhattacharya parameters. I do not have time to discuss this thing. And Reed-Muller rate profile is based on rate profiling based on the Reed-Muller code. In Reed-Muller code, we we take all these bit indices, we calculate the number of ones in each bit indices, and we rank all of them. For each, we rank the bit indices according to the number of ones in the indices, and we out from the k highest number of ones, we will fill the information bit. So that is the Reed-Muller rate profile. Polar rate profile is based on Bhattacharya parameter, which is exact the polarization thing which I explained just before. There is a metric called Bhattacharya parameter for AWGN channel. Using that Bhattacharya parameter, channels will be polarized. From the set of polarized channels, the k most polarized channels are used to construct the set of information bit indices, that is calligraphic I. Now let's say after rate profiling is done, which means we took d bits and now we have a vector of v bits. D was of length capital K, v is of length capital N, and now we have to precode. We can precode using any convolutional precoding polynomial. For example, let's say for length 7 it will be 1 0 1 1 0 1 1, and there are a lot of well-known convolutional code polynomials in the literature. We can precode them, which means each bit in V is now replaced by a linear combination of itself and the p minus 1 bits preceding it. This linear combination is decided by the precoding polynomial W. Now, as you can see in this picture, for every bit V, we are precoding it. What we are doing? We are taking W, and how many indices of W can be used to precode? From I to E, start to end, we are taking the set V. We are doing AF transpose, here means XOR in the modulo 2 sum, and we are storing them in W and U and UI. Basically what it is doing is taking every set of bits, a bit at location I is replaced by a linear combination of itself and the length p bits behind it, in front of it. After this precoding, we will do polar transform, which is normal polar encoding, and we modulate and transmit over the channel, and we get the demodulation. From the demodulation, we will generate the LLRs. From LLRs, we will go for successive cancellation list decoding. In successive cancellation list decoding, what we do is we always try to decode one bit from I equal to 0 to n minus 1. Each time we will decode, try to decode one bit, and then we will proceed. So when the bit is a frozen bit index, we know that a 0 would have been transmitted, and we give in 0 into the Vi is transmitted as UI because 0 was there, and it will not cause any precoding usage. And then we update the LLRs. After that we precode one bit. So we had this VL and we have to generate UI of L, which is actually you have to precode, because here you had a precoded thing as input. So while guessing also you have to precode all the possibilities. After precoding all the possibilities, we feed it into the SCL decoder tree. So here the UI is precoding, and update bits is taking this UI, and the SCL decoder tree is updated. Path metric is updated. Path metric is just a measure of how well a certain path in the list is doing, and we have to update it. If the bit is not a frozen bit, information bit, we have two possibilities. Either a 0 was transmitted or a 1 was transmitted. So we have to do the above thing two times, once for 0 and another for 1. I have not shown here to maintain space. Then what happens is, when we have two possibilities, the list size is doubled from L to 2 times L. But we have a memory constraint of having L possible path only. So we will prune the path according to the path metric. So the lowest L path metrics will be taken, and the list corresponding to those lowest path metrics are selected, and again the list size become capital L. So this continues. At the end of the decoding, we will have this V corresponding to the path which is best. Best means having the lowest path metric, which, since we are sorting, will always be on the top of the list. From that, we will take the information bit positions, and we will take the bits from information bit positions, and there are k such positions. From that we will get the estimated D vector, which is shown by the message extraction unit here. Now let's go to reinforcement learning algorithm for Polar/PAC code construction. As we already discussed, the problem of construction of Polar code or PAC code is that of choosing k indices out of n indices. So the concept of looking at Polar code construction like a maze traversal game was for the first time given in a paper as shown in this reference by John Schioffi and Andrea Goldsmith. So they constructed a maze which had n minus k plus 1 rows and k columns. So a robot can, each nk polar code construction was viewed as a maze with n minus k plus 1 rows and k plus 1 columns. Cells of the maze define state row column of the environment. At any time, the RL agent can be one of these possible states. So this is the number of possible states, which is modulo calligraphic s equal to n minus k plus 1 multiplied by k plus 1. So for example, if I have to construct a 32-16 code, 16 over 32, where k equal to 16 and capital N is 32, so I will have a matrix of 17 cross 17. So 17 square number of states are there. State 0, 0 is defined as the initial state, and n minus k is defined as the terminal state. So the robot will enter from here in the here, and then it has to come out at the bottom right of the maze. And there are some rules to this game, not like ordinary maze traversals. They stated that the agent can take only two possible actions, either a down action or a right action. For each episode, the agent is required to start from the initial state, which is 0, 0, and end up terminal state by taking a total of capital N steps. At each step, the agent is required to select one of two possible actions, down or right. If it takes the down position at kth step, then we think that kth bit is considered to be a frozen bit, and we will transmit a 0. If the agent select right action, then kth bit correspond to a non-frozen or information bit position. So by playing a lot of games, the agent has to learn which is the best path uh, uh, from top left to bottom right, which increases its survival chances in the maze. Now, where from this question of survival is coming? Here is an example of the robot trying to traverse. It can, I will explain why the question of survival comes. So, each time what we do is we will transmit an all zero code word through the channel. So when we transmit all zero code word through the channel, on the decoder side, we know that we should receive all zeros, but we don't know which among these zeros was an information bit, which was a frozen bit, and we actually do not care about it. What we do is we try to decode each bit using successive cancellation decoding. Now, if in the successive cancellation list decoding among the list, the all zero code word is removed, I mean none of the path in the list have all zeros, there is at least one in each of the paths, then we think that the robot created a very uh, grave mistake which leads to termination of the decoding, which means that the robot is killed there. So, and we are transmitting the bits at a certain SNR, so noise will be changing. So this is a stochastic maze where at each position noise can kill you. At a given SNR, you have a certain survival probability. So the robot has to increase the chances of its survival from top left to the bottom right when under noisy conditions. We will add noise to the transmitted all zero code word. Here is the main contribution of our paper. Compared to there is only one paper in the literature which does this thing until now, and they only do it for polar codes, and we try to reproduce their work, but we found some problems, mainly with respect to learning polarization codes or CRC aided polar codes. We think there is a lot of work to be done. Our first and main contribution is reduce the search space. Here you can see the search space is very big. Can we have some domain specific knowledge from what we know from the coding theory of polar codes to reduce the search space to help the agent make lesser mistakes? That is point number one. A method of reducing the search space for RL agent by using known properties from coding theory such as the RM score. RM score refers to the total number of ones at given bit position, which actually, if we consider a generator matrix, will correspond to that bit index which is having higher Hamming weight. Higher Hamming weight will lead to code words having bigger Hamming distance, which means these code words are separated more and more in the three-dimensional space. So it is more likely that the decoder will make less mistake, which means there will be less decoding failure, so the performance of the code will improve. And secondly, we introduce for the first time in the coding theory literature a new set of reward and update strategies which help the reinforcement learning agent discover much better rate profiles than those present in existing literature. So we can confidently say that our rate profile constructions as of date are the best possible rate profile constructions for polar codes as well as polarization adjusted convolutional codes, and which we will prove by simulation results, and our results have been cross verified by other universities as well. So we have got citations recently. Let's go to Q learning for polar code construction, where the input is the length n of the code word, the key information bit, the precoder W, and the length of the precoder P. Output is the Q matrix. So as we do in Q learning, we will get a Q value for each state in the uh, maze, and according to the q values we take, if the best q value tells that we have to take a right action, we will take a right action. If the best q value is for action down, we will take action down, and so on. Based on the q values, we will traverse from top left in the maze to bottom right in the maze. So q values is state action pairs, and we index them accordingly for easy of programming. We have a certain number of episodes. We have a discount factor. We consider a discount factor of 1 here. The main reason being the robot has to go from the top left to the bottom right, and it has to consider to improve its chances of survival along the whole path. So discounting factor will be 1, but we are still experimenting and trying to find out if other discounting factors can help us improve our algorithm. The learning rate can be adjusted, but mostly we are taking standard value like 0.1, and exploration rate epsilon in this algorithm, where it has to do epsilon times like 0.1. 10% of the times the robot will explore new strategies, and 90% of the time it will do based on the best q value, which is an epsilon greedy approach. Now let's go to the core of the q learning algorithm. What happens in each episode? So the state S is initialized to initial state, and we first get an initial rate profile, which we will discuss, and then we take an action. We will take an action. We will store this action at the kth bit, where k goes from 0 to n minus 1, and based on the current state and the action, we can go to next state. Now at k equal to 0, if it is the first time, we will transmit an all 0 code word through the channel, and for the rest k from 1 to n minus 1, whatever this code word was transmitted, we will try to decode it. Let's say I took an action 0, which means a frozen bit. I think it is a frozen bit. Decode the kth bit as if it is a frozen bit. Update the path metric list and survival path. If it is not a frozen bit, it's an information bit, we will decode the kth bit as if it is a non-frozen or information bit, and will update the path metric and survival path. Now, since we took a information bit, we have to check whether the all 0 code word that was sent is surviving in the list or not. If it is not surviving in the list, we give a reward, which is a very negative reward, and we update the q values accordingly. We terminate the decoding by setting the terminate flag f. If it is not the case, then we don't terminate, and state S is transitioning to next state S dash, and this continues till either the episode is killed, the robot is killed in the episode, or the robot survives and reaches to the bottom right of the maze. And the robot plays this episode a lot of times, not as a lot of times as in big games like Atari games or anything, but here we can do it within 20,000 to 50,000 episodes. If f equal to 0, it is not terminated. We are getting the index of the all 0 code word in the path metric list, and this is the index, like due to wrong decoding or the wrong rate profile choosing by the robot, it is possible that the all 0 code word goes down in the list and may escape from the list and be dropped from the list at any time. So we are taking care of the index of the list, and we are also taking the get the first code word from the path metric list, which is the code word at the top of the list, which will actually be the output of the decoder. Now what we are doing, for each k equal to 1 to n, we are taking the kth action and we are taking the state. We are giving reward for each bit index, k, and we are updating the q values accordingly, and then the state transition happens. Now this is which is happening at the end of each episode. After, if the robot has survived only, we are doing this one. So we are giving it kind of rewards, which we will discuss later. As you can see, this is not exactly Q-learning. Probably it is kind of a modified Q-learning approach. We will discuss reward and update strategies in a bit more detail in some minutes. We discussed about initial rate profile. How to design initial rate profile, which is the first contribution of our work. How to reduce the search space. So in order to reduce the search space, we propose to build an initial rate profile based on the RM score corresponding to each of the capital N indices. Now RM score generation strategy sort the RM scores of the N indices in ascending order. Now we are checking all the RM scores have been sorted. Now I have a length of N, out of which there are k bits which are information bit, N minus k bits are the frozen bits. So from N minus k to N will be the set of information bit. So we think the N minus kth bit is our deciding RM score or the boundary RM score. Now we can divide the set of N indices into three subsets. First, the RM score of which is less than the boundary RM score, the set of indices whose RM score is greater than the boundary RM score, and the set of indices whose RM score is equal to the boundary RM score. So this code just tells what the previous page had written. Now for the set of indices whose RM score is less than the boundary RM score, these are the bit positions which we know from the coding theory literature will prove bad. So we ask the agent to take a down action. We encourage the agent to take a down action. In these conditions, if it takes a right action, it is heavily penalized. For the set of actions, indices whose RM score is greater than the boundary RM score, we know from the coding theory literature that these are the places where the code word will have a high Hamming weight, and the agent should take a right action. So we encourage the RL agent to take a right action in these indices. We penalize it heavily if it takes a down action. So based on this, we create an initial rate profile and denoted it by calligraphic I in it. So it is possible that the length of the number of bits chosen in the initial rate profile equal to k. In that case, we have to do nothing, no need of the RL algorithm. It falls back to the Reed-Muller rate profile. But we can have situations where I init, the modulo I init, the number of bits chosen in the initial rate profile is strictly less than k. So we have that many bits to choose. So in the second phase of the algorithm, we will take the action generation algorithm, select the k minus modulo I init indices from the available modulo n indices. So the set of the indices where RM score is equal to the boundary RM score will be denoted by calligraphic n, and let's say, for example, I am trying to construct a 6432 code. In this case, the boundary RM score, which is 8, will have 20 indices, and the 22 indices will go to initial rate profile, and I have to construct a 6432 code. So 10 indices remaining I have to choose. So I have to choose from 20 possible indices, I have to choose 10 indices. So my problem is reduced from 64C32 to 20C10. For this set of indices, the agent select the action A from current state S using a policy derived from Q, that is epsilon greedy. So this is the proposed action generation algorithm, which we basically described. Uh, we are if we have chosen all the information bit positions for this episode, we have no other option but to go down. Similarly, if we have chosen all the frozen bit positions, we have no other option but to go right and make everything a information bit position. In other cases, we can take a action based on epsilon greedy, and we remove it from the set of frozen bit indices, and we increment on the initial rate profile, and so on and so forth until we get the all the actions. Now the reward strategy. If all zero code word survives in the list while decoding through successive cancellation list decoding, that is f equal to 0, we did not terminate. Value function q for the given state action pair of all the n state action pair taken during that episode are updated. Now this is very different from what happens in normal Q learning. Normal Q learning, we immediately update then and there for that state action pair. Here what we are doing is kind of experience replay, where if all zero code word is surviving in the list, we are traversing the maze again, whatever has happened, and we are giving some delta reward to each of these bits. Reward for the kth state action pair depend on two factors. First, it depends on the kth output bit, either it is a 0 or a 1. Kth output bit is from top in the list. Second, it depends on the index in the list where the all zero code word is present, if not dropped from the list. We call this index as all zero code word index and denote it by I. Now, a bit ck is there, which is from the top in the list, which is, and another thing is there, which is the all zero code word index. At that all zero code word index, definitely we have all zero code word vector. We will see how much difference is there. A positive reward of x is defined as base reward is given if kth bit is correctly decoded, which means it is decoded as a 0. Otherwise, a negative reward of minus x is given. So x and minus x, these are kind of single time tuning values based on the length of the code. Based on all zero code word index, the reward is dropped by an amount of z of I minus 1, where z is known as the step reward and I is the index of all zero code word in the list at the end of the episode. So let's say if all zero code word is there somewhere in the list, but it is not the best one, so the reward will be x minus z of I minus 1. Similarly, if it is wrongly decoded, minus x minus z of I minus 1. Also, if the kth bit position correspond to the first bit error, which means the decoded bit was decoded incorrectly, we give a further delta negative reward by an amount x. So, whatever we are doing here, the main intent of the proposed reward strategy is to make the RL agent learn rate profiles which will help to keep the path with all zero code word as high in the list as possible so that it becomes the best path. So what the RL agent is trying to learn is how to push the all zero code word as up in the list as possible, while the all zero code word is bowing up in the list, going up and down and up and down. The RL agent is trying to learn how to keep the all zero code word as top in the list as possible. This is what is the main differentiating reward strategy, which has been first time proposed in the literature in this work, and it works very well, as we will see. So the update strategy is like if similar to the normal Q learning update strategy. If Q of state action pair is dependent on the previous state action pair plus the product of the learning rate alpha and the reward plus gamma, which is the discounting factor. Q of S dash is the next state, and 1 if we have exhausted all the frozen bit positions, we can go only right. And in this case, we have exhausted only all the information bit positions, and we can go to next only down positions. In other cases, state action, next state and next action would have been taken. We are checking which is the best among the Q values, and we are updating Q based on it. This is a normal temporal difference part of the Q learning, where the special conditions arise due to our efforts of not letting the agent try to make mistakes. Means more mistakes. Definitely it will make mistakes, but we are trying to reduce the mistakes. Now this is an example how the robot would go. Let's discuss some simulation results. First, we try to construct a 6432 PAC code, and there are a lot of curves here. The black color curve is CRC aided polar code, which is currently standardized in 5GNR, and we tried to simply use the rate profile which is given in the 3GPP specification 38.212 to construct a PAC code. You can see the performance is very bad. So that is something we won't like to compare with. Just for the purpose of completeness, we have put this picture. Our main competitor is the work from Bill Kent University, which to the best of our knowledge is the rate profile construction present in the literature, which is the best among whatever we have compared. So as you can see, our PAC code construction based on the proposed algorithm marginally beats, say, the PAC code construction by the reference from Bill Kent University by a comfortable margin at almost all the SNRs. Now let's see what happens if we increase here the list size was 8 in the first figure. We increase the list size to 32. When we increase the list size to 32, the Bill Kent work, which is a blue curve, is also performing very good. But when the high SNR is coming, according to 10 to the power minus 6, these curves are like 1 crore number of blocks have been simulated to generate this one. So as the high SNR conditions, the gap between our construction and the construction from the competitor increases, and that is why we think for URLLC high reliability low latency systems our construction is well suited. Now this is 12872 polar code constructions. The literature does not have this construction, and this is one of the trickiest parts in PAC code construction, and probably that is the reason we don't find much results in the literature for this one. So as we can see, polar code based on 5GNR and PAC code based on 5GNR are performing very bad, and however a simple polar code by the proposed algorithm, where we considered that the W matrix is identity matrix, is performing much better. And if you make a PAC code on top of it by using the precoder 1011 and 011, it is performing very good as compared to the 5GNR. And to be frank, the reference papers which we have used do not have this 12872 code. I think we are the first guys to show 12872 code in the literature. Now we want to check what is the impact of changing the precoder. Arikan in his 2019 lecture, he told that the precoder anything can be used and it does not have that big impact as the rate profiler. So here is our thing. PAC code from 5GNR specification is actually very bad. The Bill Kent construction at L equal to 38 and our proposed constructions, we are beating them at almost every SNR. However, their code we believe was optimized particularly for this one and for this one. So we believe the effect of having a good precoder is very important. As we can see here, no matter which precoder you use, our performance is better than the best possible rate profile design which is present in current literature. So this is also for 6432 code. Now let's go to 256.128 code, which is not short codes, but we call them as moderate length codes. So as we can see, the black curve and the blue curve are given by Bilkent University's rate profile construction at list length 8 and list length 32. So when we use list length 8, we are beating the rate profile construction of Bilkent University, and we are also beating them at L equal to 32. Probably if we use higher list length, we will beat them by a more comfortable margin. However, as you can see, we are beating them comfortably by around 0.252 dB at every SNR, which for AWGN channel is very big difference. Improving 0.1 dB, 0.2 dB on AWGN channel is not a small thing in the literature. Even 256.128 codes, also we are beating the reference. And now here we would like to emphasize that we have reproduced these works from the mentioned research papers, and we first validated our work by reproducing the research work from research papers. We matched and cross-referenced their work, sent them our results, and we got confirmation from them that we are doing the right thing. And after that, we proceeded with this algorithm development. So it is confirmed that the curves that we have presented here are working and will work even if they are made in hardware. However, the best advantage with rate profile construction is they are a set of bits which can be easily programmed in firmware. There is no need to change hardware for this one. Second advantage is we have focused on improving the PSC code constructions, rate profile constructions on smaller list length like L equal to 8 or L equal to 32 and not L equal to 128, which is very big. So our main aim is to improve the PSC code construction for lower list length so that they can be easily adapted by standard bodies, because we cannot convince people to have L equal to 128 list length SCL decoder is not possible, but L equal to 8 and L equal to 32 is definitely possible in 3-4 years, considering that transistor density is doubling every 2 years according to Moore's law. Now we come to the conclusion. In this work, we presented modified Q-learning algorithm for rate profile construction of PSC codes. We demonstrated that PSC codes constructed by using the proposed algorithm perform better in terms of FER compared to the PSC codes constructed with rate profile designs in existing literature. By existing literature, we compared with the 3GPP specifications and the best possible constructions that was provided by Bilkent University to the best of our knowledge. And we did compare with constructions given with Monash University and with some Chinese universities, also from University of California, San Diego. But comparing all those constructions, we found that Bilkent is already performing better than all of those papers. So we thought we should directly compare with Bilkent and prove ourselves better than that. We also showed how the choice of convolutional precoding polynomial can affect the performance of PSC code. And there are some open problems. RL algorithm may terminate at a locally optimal solution given how you tune. So it sometimes might lead to poor construction of PSC codes. So one possible problem statement that we can think of for the future work is how to get the reinforcement learning algorithms can advanced learning algorithms like deep Q learning, or we can tune some hyperparameters for Q learning itself, or we can use some actor critic methods to design rate profiles. Now, these are some things which we have kept for future work. Secondly, we have taken a convolutional precoding polynomial and designed a rate profile for it. Let's reverse the question. For a given code rate and block length, does there exist a convolutional precoding polynomial for which FER at a given SNR is minimum? So we are trying to check the effect of the convolutional precoding, and we believe this is also a valid problem to work on. Thirdly, for standard compliance, we need to include effects of rate matching. Like we cannot always have codes of the length 2 to the n. We need to have arbitrary code length. So to have arbitrary code length, we need to puncture some codes, and we need to shorten codes. So can we have rate profile construction algorithms that include the effect of rate matching? With this, I would like to conclude and thank you all for listening. And if you have any questions, please do write to us or on the given email, and we will be definitely happy to hear from you. Thank you so much.